Hello, welcome back. Before the unit test, better we complete the bonding homework sheet discussions because today discussion will be important to answer some questions in the unit test. Okay, let's go to the discussions. I can't remember exactly what the question I gave. I mean, A-level 2021, fourth question I think we did in class. A-level 2022 structured essay question also we did. Then today we will discuss the rest of the other questions. First, I go to 2020, A-level 2020, third question. First question given in the tute. Sorry. This is A-level 2020, but third MCQ. M is an element that belongs to the second period. When I say second period, it's from lithium to neon. Second period in the periodic table. It forms a covalent molecule MCl3, which has a dipole moment. They ask the group of the periodic table. So when you have a formula like MCl3, the valency of M here is 3 because M has formed 3 bonds. Chlorine valency is 1 when it is a surrounding atom. The M has valency 3. What are the groups you can have valency 3? We summarize that under periodic variations. I mean the periodic table in unit 1. Group 1 valency 1, group 2 valency 2, group 13 valency 3, group 14 valency 2, 4, group 15 valency 3 and 5, group 16 valency 2, 4, 6, group 17 valency 1, 1, 3, 5, 7, group 18 noble gases. So according to that, I mentioned the valency 3 in 3 groups, group 13, group 15 and group 17. Let's consider all the possibilities. If it is group 13 element, you know MCl3 is something like this. Sorry. 3 bonds available, there is no any lone pair. Shape is trigonal plane. Shape is trigonal plane. If it is group 15, you know, it forms MCl3 types like this, but M is group 15. There are 5 total electron, 3 invalid bond in. There should be 1 more pair. What is this? Trigonal pyramid. Trigonal pyramid. But if it is group 17, it can make the bond like, the formula like MCl3 like this. But can you see that when it's group 17, 7, there are 3. Then there should be 4 more. 3 bonded pair, 2 lone pair. 3 and 2, you know, it is T-shaped. Got it? Trigonal planar, trigonal pyramid, T-shape. Those are the shapes possibility. But they say which has a dipole moment. This molecule has a dipole moment. So if it has a dipole moment, the molecule should be a polar. If it is a polar molecule only, it has a dipole moment. So I gave you the set of molecules or the shapes that can be non-polar and the set of shapes that can be polar. This says has a dipole moment, mean it should be a polar. So when you consider this 3 structures, trigonal planar comes under non-polar category. Right? Trigonal pyramid comes under polar category. This one also comes under polar category. So it has a dipole moment. If it has a dipole moment, it should be a polar. If it is polar, it could be group number 15 or group number 17. Group 2, no. Group 14, no. Group 13, no, not possible because group 13, non-polar, no dipole moment. Group 15, yeah, possible. Group 16, not possible. Then according to that, group 15. Fourth one should be the answer for this question. Next, A-level 2020 MCQ number 4. It's about the resonance structures given. You are given a structure HOO in double bond O minus plus. Right? This is a dative covalent bond. These are the lone pairs available. Right? And this has 2 pairs and this has again a 2 pair. Right? This is how we get the structure. Now you are asked to draw these Lewis structures for this ion, not ion molecule. and you have to find out the unstable Lewis structures. But before you draw it, you need a plan. You have to find out what are the positions you can have double bond. One position is already given. I normally label that one as the first place. Can we have double bond here? Yes, because there is lone pair. Can be donated, make double bond. Can we have double bond here? Yes, there is lone pair. Can be donated, make the double bond. Can we have double bond here? Yes, there is lone pair. Can be donated and make the double bond. So therefore, one is already done, but you can draw three more structures, keeping the double bond to second place, third place, and fourth place. Right? Now I draw them and show you what are the stable and unstable structures. You see, this is the skeleton we have in the next case also. But if I want to make it in second place, you know what to do. This lone pair should be donated, make the bond. And thereafter, this pi bond should be broken towards oxygen. That's the way we draw it. So according to that, this should be a double bond. Sorry. This should be a single bond and takes electron pair. This has two pairs. Three were there, but one donated. Now it's only two remains. These two not change. This is the first structure. And when you consider the charges, middle nitrogen does not change, but this oxygen should be minus. Sorry. You can apply that formal charge rule and find it out. Second place, okay. Now I move to third place. I want the double bond to third place. Sorry. Then skeleton does not change. NOO like this. But I want to make the double bond here in this place. For that, this lone pair should be donated and make the pi bond. But in that case, this pi bond should be broken towards this oxygen. So as a result of this, this oxygen takes another pair. It becomes then minus. Middle nitrogen doesn't change. This oxygen already minus. Three pairs available. This oxygen donate lone pair and make the double bond. One lone pair and plus should be here. And a lone pair. This is the other structure we can draw. Thereafter, I take the double bond to fourth place. To get the double bond into fourth place, this lone pair should be donated. And this pi bond should be broken to the same side. Then skeleton same. If I draw it, you can see it. Hydrogen, oxygen, nitrogen, oxygen. That's how we have it. But now this is donated mean this bond is double bond. One lone pair donated, one remains because of that plus. Middle oxygen does not change. It already has plus and lone pair. This nitrogen take electron and minus, electron pair minus, but already plus, then neutral. This oxygen minus three pairs. This oxygen minus three pairs. That's how we have the fourth structure. If you keep double bond to fourth place. Got it? These are the structures we can have. Now you are asked to identify the unstable structure. You see the charge separation. If it has more charge separation, that is unstable. Next thing, if you have plus charge on more electronegative atom like oxygen, halogen, definitely unstable. Next thing, if you have two adjacent atoms having same charges, plus, minus, definitely unstable. Those are the things we discussed. So what about this? It's just plus one, minus one more electronegative. Plus one, minus one more electronegative. Plus, minus, more charge separation. Plus on more electronegative atom. Adjacent atom plus. Definitely this is unstable. This one, plus, minus, on more charge separation. Plus, both positive charges are on oxygen, definitely unstable. Then how many unstable? Compared to them, these two should be definitely stable. These are stable. Then there are two unstable structures. So answer should be second one. Question number 4, A-level 2020, question number 4, answer should be second one. There are two unstable structures. Got it. Thereafter, we move to the essay A-level 2020 essay question 1B. Yes, 1B. First thing is given to draw the most acceptable Lewis dot dash structure for the iron N2O3 2 minus. It's given N2O3 2 minus. Overall charge is 2 minus. Skeleton is given for convenience. It's like this. Into 2 minus should be there and N2 should be there. So where do you place minus? We normally place minus on oxygen, this one and this one. I can keep this one minus and this one minus, but in that case, I know it is unstable because my target is to get the double bond here. When you get the double bond here, it's neutral, less, I mean the charge separation minimum. So if you keep minus, this is single, then to make nitrogen valency 3, this is single, this should be double bond. But in that case, it's definitely unstable because if this is double bond, this nitrogen cannot have again a single, because there are 4 electrons in all, one should be unpaired electron should remain. I hope you can imagine it. Then there are more than 8 electrons, unstable. So if you keep here dative covalent bond, then plus, minus, minus, you see plus, minus, minus, more charge separation, unstable, right? So therefore, that is why I decide minus should be on this oxygen because most of the stable structure. If this is minus oxygen single, this oxygen should be double. Then we complete the other electrons. Once you complete the other electrons, what do we have? Oxygen has 2 more pairs because total should be 6. 2 in bonding. This nitrogen should have 1 more pair. This nitrogen 3 given mean 1 pair. This oxygen minus mean 3 more pairs, 3 more pairs, 3 more pairs. This should be the most stable Lewis structure for this one. Right. Then they ask this one, draw 3 more Lewis dot dash structures for this iron, indicate the relative stabilities of the structure drawn by you when compared with the most acceptable structure one by writing less stable, unstable. This one is the first one, then we take this one as a stable one. Compared to that, we write less stable, unstable for the other 3 structures. But in that case, first we have double bond here. Then you can have double bond here because lone pair available can be donated. Then you can have double bond here because lone pair available can be donated. Then you can have double bond here because lone pair available can be donated. Then 1 is already given. Then 2, 3, 4. Those are the 3 structures we have to draw. Now by keeping the same skeleton, we change the position. In that case, I think I need to erase this one, but before that, let's keep it here. O, N, O, N, O. That's the skeleton. Now I want to change the position of double bond to second place. For that, this lone pair should be donated and make the pi bond. Then only it becomes double. But to the same side, it should be broken. Now then, this is broken mean, this is lone pair minus. Middle nitrogen does not change. This becomes double bond. This nitrogen donate lone pair becomes plus. These oxygen do not change. These oxygen do not change. That's the next structure we can draw. You see, overall charge always it should be minus. Ne? Plus minus cancel. -2. It should be -2. Yeah. Then plus minus cancel. Minus minus -2. Okay. Thereafter, I draw another structure by taking the double bond to third place, this one to this one. For that, I keep again the skeleton same in O, this is N, and again O. What I do, the position of double bond should be here broken. Sorry, before that, we have to make the bond. Sorry. Then this lone pair is donated, make the bond. This pi bond is broken to the same side. Same story. Then 2 remains and double bond. Middle nitrogen doesn't change. This double becomes single. It takes another pair. Becomes minus then. This is also minus. It has 3 pairs. This oxygen, no change, it's again minus, still minus. That's how we get the other structure. I hope you can see. These two interchange. Now I have one more structure to get the double bond to this place. For that, we have to give the lone pair here, make the double bond, then this bond should be broken. We have the same skeleton in ONO like this. Donated, 2 remains and double, good, double, sorry. Middle nitrogen does not change, plus this single broken, new lone pair added, then minus, you see. That's how we have it. This nitrogen, no change, you get minus. This one lone pair, yes, and minus. This is the other structure we can have. Can see, is it clear? Right. How to compare the stabilities? That is the question next we have. We take this one, the first one as the stable one, this one. With respect to that, what about this? Here minus minus, only two sides. Here minus 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 plus, more charge separation. Here minus minus plus minus, more charge separation. Here also minus 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 plus, more charge separation. Definitely they are maybe unstable, maybe less stable, but we have to find out which one is the, they are less stable and unstable part. So which one? Negative oxygen plus on nitrogen, okay. And negative oxygen plus nitrogen minus nitrogen. You see, nitrogen. If it is nitrogen, they can't have plus minus. Nitrogen means same electronegativities. And next thing, adjacent atoms have negative here. Unstable. So therefore, you definitely identify this structure as an unstable structure. What about this one? Here also same story, minus. Plus minus, okay. Then this one also unstable. What about these two? Then what about this one? This should be definitely less stable. According to your structure, see which one is unstable, which one is less stable, and which one is stable. Definitely stable one is the one we drew first. In the case of third part, you are given a stable structure. Now you asked to get the whisper and all this stuff. Actually, we did these things in the class also. So I hope now you are okay with this type. We did that several times. Double bond in, lone pair, O, C triple N. That's the structure we have. So they ask whisper around N1. N1 mean this one. I take it like that. First one, whisper. Simply write VACPR. So VACPR is based on number of sigma bonds and lone pairs. So we get sigma, double mean 1 sigma. There is no lone pair. So it should be total 3. Around this is N2. Around this nitrogen, sigma, lone pair, total 3. Next one, O3, this one. Yes, around this oxygen, sigma, lone pair, total 4. Around this carbon, finally. Yes, sigma, only 2. Okay, these are the VACPR. Then electron pair geometry. So electron pair geometry based on the number of repulsive units. This information actually available in that table I gave you. So 3 means, what about this? Trigonal plane. 3 means again trigonal plane. 4 means definitely tetrahedral. 2 means linear. We are talking about electron pair geometries. Thereafter, shape. To decide the shape, you need total bonding pair, lone pair. This is like 3, 0. No need to write 3, 0, but I show. Trigonal plane again. This one is like 2-1. 2-1 mean definitely angular. This is 2-2. 2-2. 2-2 mean definitely angular. I don't write full word, angular. This is 2-0. 2-0, yes, linear. If there is no lone pair, you see, if there is no lone pair, the electron pair geometry shape same. Next one, the hybridization finally. Hybridization again based on VSEPR. Yes, 3 mean sp2, 4 mean sp3, 2 mean sp. That's how you complete that table. These are quite easy, so quickly we decided. Fourth part is identify atomic or hybrid orbital involved in the formation of sigma. So sigma means the linear overlapping. In the case of linear overlapping, all the orbitals, I mean the atomic orbitals can linearly overlap. Hybrid orbitals can linearly overlap. Atomic and hybrid also can also linearly overlap. Any type of hybrid atomic can linearly overlap. But in that case, you need to know if you have like PY, like parallel like this, then can't be linearly overlap. If you have a PZ, then they are again parallel, can't be linearly overlap, lateral overlapping. If you have P and D, lateral overlapping, D and D, lateral overlap. So therefore, but we don't have those things. I mean, the DD we don't have in our syllabus. All right. Then chlorine N1. Chlorine N1 mean this one. Then we are talking about this sigma bond. In the case of this sigma bond formation, you know, chlorine terminal. In the case of terminal, you can, the other thing is that one, if it is a terminal one, not central, then you can consider either hybrid or unhybrid. You're safe to find it out, hybrid or unhybrid. If it is hybrid, you can see 1, 2, 3, 4. I mean 4 VSEPR, then sp3. If it is unhybrid, you know, when you write the configuration, you will see unpaired electron available in 3p. So it should be 3p or sp3 in the case of chlorine. Right? I roughly write it here. This is the fourth part under that first one. So chlorine, someone say sp3, okay. But N1 definitely hybridize sp2, whether sp3, sp2, or someone can accept it like 3p, 3p, sp2. Remember 3p, eh? You can write the configuration for chlorine, 17, atomic number 17 mean 1s2, 2s2, 2p6, 3s2, 3p5. You see, there are unpaired electron available in 3p. Therefore, it's the atomic orbital that overlap with sp2 of N1 linearly in the formation of sigma bond. That's the story. So likewise then, N1O1. Next, second one, N1O1. N1O1, then this one. O, again, terminal. This oxygen, N1O1. Yeah. N1O, yes, O, N1O. Oxygen also terminal. Then if it is terminal, can you see that there are 1, 2, 3, 4. 4 mean sp3. Or when you write the configuration of oxygen, you will see it's 2p4, means atomic orbital is 2p. So now you can write N1 definitely hybridized. So it should be sp2, sp3, or sp2, 2p, any of this. Third part, N1, N2, both are hybridized. Then in the case of linear overlapping, they must be hybrid orbital. N2O3, N2O3, maybe this one, N2O3, yeah, that's the case, N2O3. Both are hybridized. So in the case of sigma, they must be hybrid. That means sp2 and sp3. Fifth one, O3C4, both are hybridized. So in the case of sigma bonding, they must be hybrid orbital. Then if these are hybrid. Yeah, what about that? sp3, sp. sp3, sp. Sixth one, C4N. I write it here. Yes. Sixth one, C4. C4 hybridized. That's sp definitely. But terminal. Then one can see the two VSEPR. Sigma lone pair, two VSEPR mean sp. Or when you write the configuration, you will see it is 2p3, the valence shell. Therefore, it should be 2p. So in this case, you can say SP or SP and 2p. That's how we answer that question. Right? It's not difficult, very simple. Identify the atomic orbital involved in the formation of pi bond. The next one, that's another easy one. In the case of pi bond, you get lateral overlapping. Then in the class that day, I told you lateral overlapping possible between py, between pz, like this, lateral overlapping. py, pz. What else? P and D also possible. D double dumbbell, like this. PD can partially overlap. Even DD can partially overlap like this. These things. So therefore, if they ask pi bond, it's most probably py, pz, sometime P and D, sometime D and D. But in the case of this, we don't have D and D. In one case, I saw in one past paper question, I saw PD they check. It's phosphorus and oxygen something. PD they check. PZ, and PY. Those are available here. But again, they don't expect this Y and Z that part. Just you say the corresponding P. I mean, maybe 2P, maybe 3P. Just mentioning that one will be enough in this case. Hurry. Now you see, first N1, N2, there is a pi bond. But nitrogen, what's that P? It is 2P. Therefore, in this case, it should be N1 2P, the other nitrogen also 2P. Second part, it says C4N. Here you see there are two pi bonds, right? Since carbon sp, only one P involved in hybridization. Let's say PX involved in hybridization. So then PY remains and PZ remains. So with nitrogen also, you see, if it is hybridized, the nitrogen also sp. If it is sp, then 1p only involved in hybridization, we can say it is px. Then py available, pz available. Py of nitrogen and py of carbon laterally overlap to form one pi bond. The other one, pz of nitrogen and pz of carbon laterally overlap to form the next pi bond. But in this case, just write in 2p enough. You don't have to write 2py, 2pz, 2pz. Just 2p. Enough here. Thereafter, you have the sixth one, state the approximate bond angles. In the case of bond angles, we know again, we discuss under the shapes and everything, geometry. N1. What about N1? N1, you see the trigonal plane and electron pair geometry, trigonal plane. Then we expect 120. Here, the shape also trigonal planar, then maybe 120. But the thing is this one, since the repulsive units here different, oxygen, nitrogen, chlorine, there may be different repulsive forces. Therefore, one angle will be slightly less than 120. Another angle should be slightly greater than 120. These are possible. Because of that, in marking scheme, they accept this one. 120 plus or minus 1 accepted. I'm talking about N1. N1 case, 120 plus or minus 1 possible. That means if you write 119, correct. 120, correct. 121, still correct. N2. In the case of N2, we get this one. This is N2. It's trigonal planar. 120 we expect. But shape, you see, because of one lone pair, the shape is, the shape is angular. Then the repulsions increases here. You know that story. Lone pair, bonding pair repulsion stronger. In that case, bonding pair repulsion weak. Therefore, bond angle definitely decreases. Then I told you just take subtract 2 decrease if there is one lone pair. 120 we expect, but 2 decrease mean 180. Okay. But this is level 2020. In that marking scheme, they have given any value between 115 and 118. This is what they have given. So you write 118, correct? But it's not like 118 plus or minus. I don't know why, but once we go to the other marking scheme like 2023 and everything, then again they come back to the normal one, 118 plus or minus 1. But in 2020, they accept values 115 to 180. 118 also correct. O3 means this one. Tetrahedral mean we expect 109, but two lone pairs. Two lone pairs mean 4 degree. 109 minus 4. I'm talking about O3. It's 104. But again here, plus or minus 1 accepted because repulsive units are different. Next one, C4, SP, linear C4. Then we expect 180. But again, plus or minus 1 because repulsive units are different. These are the accepted answers. Last question given, arrange the atoms increase in order of electronegativity. But in this case, I told you to understand this, we need the oxidation state concept. Since we have not done oxidation state part, I will not explain this one. So once we complete oxidation state, I'll come back to this and then explain. Don't worry. For the unit test also, I will not include this question. Once I complete oxidation state, I will definitely come back to this and explain it. Therefore, I just skip that one. So this is how we answer that question. Hurry. Next, A-level 2021 fourth question we did. The next question we did in the class, I remember. Let's jump to 2021 eighth question, the MCQ one. Okay. Hurry. I'm going to erase this. A-level 2021 eighth question. MCQ. Select the correct statement. They ask correct statement. Electron pair geometry and the shape of SF5 plus are different from each other. You know, then electron pair geometry and the shape, those two are equal if there is no lone pair. If there is at least one lone pair, the electron pair geometry and shape should be different. Now the question is, draw in this structure and then find in whether you have a lone pair on sulfur. Let's do it. SF5 plus given. SF5. You know, fluorine valency 1. So there are 5 fluorine with 5. Sulfur 16, 6. Then 1, 2, 3, 4, 5 and 6. This is SF5. But it's given SF5 plus. Plus removing. Definitely this electron should be removed. This should be SF5 plus. Right. What about the number of lone pairs? Do you have lone pairs? You don't have. If you don't have lone pairs, then electron pair geometry and the shapes are equal, same. But this says different. Can't be the answer because they ask correct statement. You asked to find out correct statement. Okay, next. Increase in order of radii atoms F minus, Mg2 plus, aluminium, Cl minus, potassium is given. It's definitely incorrect because you see, the ions you are given F minus and Mg2 plus. Yes, look at in these two only you can understand it. You know, atomic number 9, F minus mean 10 electron. Atomic number 12, Mg2 plus mean 10 electrons. So what are these things? These are isoelectronic species, I told you. For isoelectronic species, I said radius is inversely proportional to number of protons. Same number of electrons mean you have same configuration, same number of energy level. We expect same size. But what if the nucleus is highly positive? If the nucleus is highly positive, definitely electron clouds shrink because nucleus will pull that electron cloud strong. That is the case. Then proton increase, nuclear charge increase, radius decrease. According to that, you know, Mg2 plus is smaller than F minus. But in the answer, it's given Mg2 plus greater than F minus. So therefore, just by considering this, you can say it's wrong. But if I just continue it, You have aluminium, Cl minus, potassium. Then aluminium definitely larger because those that is in third period. This Mg2 plus F minus, those go to definitely second period. You remember that 10 electron. Once I come to aluminium, 13 atomic number, configuration 1s2, 2s2, 2p, then 2p6 and 3s1, 3p1. Here 10 electron mean up to this only, but 13 mean 3s2, 3s2, 3p1. Then aluminium definitely larger than these two. Next one should be aluminium. After that, you get Cl minus and potassium. Wait a minute. Cl minus. Yeah. Then again, come back to this sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine. That's how normally we have. Actually, these are not the sizes, sorry. These are not exact sizes, but what I'm saying for showing here, once you go from sodium, magnesium, aluminium to chlorine, the size decreases. Atomic radius decreases. But it's not Cl, it's Cl minus. Cl minus means negative anions. Again, I told you, once you add electron to atom, the size of electron cloud increases. Now the question is whether these sizes then where do you place the new size? That's the case. So it will pass this aluminium, or it's somewhere here, it is somewhere here. You're not sure. In that case, remember, adding electron or removing electron will make a big change. Significant change is there. But in that case, I think I remember this one. I gave you in the printed note, I gave you the sizes of ions and atom comparatively. A table was given. Then in that case, better you have these type of ideas. Right? Whether Cl minus passes this aluminium or not, you have to know that one. Actually here, yes. Right? So if I show it in IE general inorganic, so it's not then practical to memorize all the values, but at least you should have some idea which ion pass which, because we are going to have A4 chemistry. So then we need to do this. I mean, it's not easy. You see, this is what given in the resource book, and same thing I gave you in our printed note also. So what do we have here? Cl99, Cl minus 181, aluminium 143, aluminium 3 plus 53. Aluminium 143, Cl minus 181. Definitely 181 greater than 141. You see Cl minus even greater than magnesium. But Cl minus is smaller than sodium. These are the points you need to memorize. Once I come to sulfide, 184. That's greater than aluminium. That's greater than magnesium, but smaller than sodium. I think both sulfide chloride place in between sodium and magnesium. So that type of idea you need. Then here, look at this. F minus 131, definitely greater than beryllium, but smaller than lithium. Oxide 140, of course, in between lithium, beryllium. This is 146, of course, in between lithium. Easy. Nitride oxide fluoride also between lithium, beryllium. Sulfide chloride also in between sodium, magnesium. That way you can simply memorize it. Got it? So then chlorine, once you add electron, that comes in between what? This one. I said no, sodium, this one. it comes between sodium magnesium. It's greater than even magnesium also. So definitely chlorine greater than then aluminium. Chloride, not chlorine, chloride. After that, you get potassium. Potassium, even we go down. Leftmost down mean it's the largest one. Leftmost down mean it's the largest one. Now again, you may have question, then Cl minus, can't it pass potassium? Lithium, sodium, this is the potassium one. But when you go down, the size will be large, very large. You see, if I show potassium value also, potassium, yeah, 235, very large. You can see that one. This is 235 potassium, but chloride 181. So this could be the correct variation, but in that case, the given variation completely wrong. So that statement is not the correct answer. Let's jump to the next third one. Number of resonance structure that can be drawn for nitric acid is 4. Number of resonance structure that can be drawn for nitric is 4. Here, you draw the nitric molecule. We do that one under oxo acid part, you remember? HNO3 molecular formula HNO3. We draw this part for oxo acid. Thereafter, check for another hydrogen. No, no more hydrogen. Then check for oxygen. Yes, we have one oxygen. Then we keep that one with central with double bond. But in the case of nitrogen and second period element, you can't have 2, 2, and 1. I mean the double, and single. Because the electron will be now 8 and 10. Because of that, I told you the solution, it's a dative covalent bond. So this is the structure for nitric. But then look at then how many possibilities are there for double bond. Already available, I labeled it like first position. Can we have double bond here? Of course, because oxygen has lone pairs. This oxygen has 3 pairs. Can we have a double bond here? Of course, because this oxygen has 2 lone pairs. Can we have double bond here? OH. No, because hydrogen doesn't have lone pair. You can draw only 1, 2, 3. There are only 3 possible structures. Since there are only 3 possible structures, they say 4 resonance structure. It's incorrect. Third statement is incorrect. Next, we move to carbonate ion has the longest CO bond among the molecules ions. Bond length, they ask, bond length. You see this question, this type of MCQ, not easy to analyze. Why is that? First question, second question, third question, fourth question, fifth question. These are from 5 different concepts. First one with the electron pair geometry shape. Second one with the size of ions and atoms. Third one with the resonance structure. Fourth one is the bond length. And fifth one is the electronegativity. These are 5 different concepts. And these 5 different concepts, when you analyze that one, you can't do that one within 2 minutes. It's quite difficult. Only if you have a very good understanding and analyzing ability can be done. Otherwise, therefore, these questions quite difficult, mean it takes time. Bond length, I hope you remember we discussed that one at the very beginning of bonding part. I said bond length increases when the overlapping decreases between 2 atoms. I hope you remember. Single, the longest. Triple, the shortest. That's one concept you need to know. Sometime you get bond somewhere in between single and double. If you get bond somewhere in between single double, then you place that one. It's in between single double. Then you place that one here, between single double. We draw that one in this manner. Then single, you see. Clear? Triple, the shortest. Double next. Next one, the bond bit somewhere in between single and double. And the longest one should be the single bond, pure single bond. Right. The next one is the atomic radius you take. Atomic radius increases, bond length increases. Those are the factors. But you first consider this one. That order is very important. Don't go to atomic radius first. Get the type of bond, single, double, triple. All right. With that idea, I go to draw carbon monoxide. Carbon monoxide, maybe you discuss, I mean, we discussed that one. Maybe you remember. It's a PO triple bond. Carbon dioxide, you all know, it's a PO double bond. Carbonate. What about carbonate? Carbonate has resonance structures. 3 resonance structures you can draw. When you consider 3 resonance structures, sometimes this bond is single, sometimes double. Sometimes this is single, sometimes double. Sometimes this is double, this is single. Did you understand it? All these bonds have not only pure single, pure double, but somewhere in between single and double. When you consider resonance hybrid, you see that one. CH3OH, the structure like this, CH3OH. Now CO bond is pure single. Can you see that? Triple the shortest, PO double next, somewhere in between single double and single, PO single. This should be the increase in order of bond length of these species. These are very important points. Very important points. All right. Is that correct then? Carbonate ion has the longest CO. No, it's not. Longest CO bond is found in CH3OH. That's false. Fifth one, among the molecules, these electronegativity. Then, oh my God. That concept, I skip this one in several places, but now I can't skip it because that is the correct answer. All the 4 wrong, then this is the correct answer, then I should say it, but I'll say it a little bit. We compare electronegativities. In unit 1, last part, unit 1, we discussed how electronegativity of atoms changes. Fluorine is the highest. Next, oxygen, thereafter nitrogen, and chlorine approximately equal, and any other atom comes after that. Then carbon 2.5, hydrogen 2.1. So likewise, we know that one. According to that, according to the position of periodic table, we can compare the electronegativities. But the question is this one here, electronegativity of just carbon. I mean, same atom, carbon. How do we do that one? So if you're asked to compare electronegativity of atoms of same element, then there is a way to compare it. Look at this one. This is important. Right? How do we compare it? Then first thing you need to consider, see the hybridization of these atoms. If hybridizations are different, electronegativities are different. Right? Then this is how it changes. sp3, sp2, sp. That means p character decreases. In other words, s character increases. S character here 25%, 33%, 50%. We learn how to calculate it on the hybridization part. Right? The s character increases, hybridization of that atom also increases. Although it's from same atom, same element, it's not always the electronegativity equal. If the hybridization different, definitely electronegativities are different. S character increases, electronegativity increase. That's the first thing. Second thing, you consider formal charge. Second thing, you consider formal charge. That means sometimes the atom has plus, it's carbon, but sometimes plus carbon, sometimes neutral carbon, sometimes negative carbon. Then remember, if there is positive charge on that carbon or whatever the atom you consider, positive atom can pull the bonding electron stronger. Means positive atom should have higher electronegativity. Here also, the S character increase, electronegativity increase mean, what about the size of hybrid orbital when S character increase? Size of hybrid orbital decreases. When the size of hybrid orbital decrease, the bonding electron come close to the nucleus. Maybe you remember that one. We discussed the sizes also. This is sp3. This is sp2. This is sp. This is sp3, sp2, sp. So when let's say here s orbital overlap, look at this is the nucleus, this is the nucleus, this is the nucleus. Then which electrons are close to the nucleus? sp. In the case of sp, those electrons, those bonding electrons close to the nucleus. If those electrons are close to the nucleus, these electrons are strongly pulled by the nucleus. That is electronegativity. That's why sp highest. Then my plus. Actually, the next factor is the one we didn't discuss. It's the oxidation state. I just say this one, oxidation state increases, electronegativity increase, but we don't know that. We have not done what is the oxidation state. We have not done it. And I'll give the other factor also. There are 4 factors actually. Other factor is electronegativity of bonded atom. Bonded atom. When the electronegativity of bonded atom increases, the electronegativity of our atom we consider also increase. So what's the meaning of that? I take one simple example like let's say you are comparing NCl, this nitrogen, and NF, this nitrogen. Electronegativities of these 2 nitrogen. Okay? See the hybridization, first factor, same name, sp3, sp3. See the formal charges, same, neutral, neutral, no charge. Oxidation state also same here. I'll show you how to calculate later. But then 4th one, electronegativity of the other atom, the bonded atom. Here bonded atom is chlorine. Here bonded atom is fluorine. Then which one out of these 2 highly electronegative? Definitely fluorine is more electronegative than chlorine. Then when the electronegativity of bonded atom increases, the electronegativity of atom we consider, nitrogen is the atom we consider. The fluorine more electronegative than chlorine. Therefore, this nitrogen is more electronegative than this nitrogen. That's what I mentioned. That's how we compare the electronegativities of atoms of same element. Different elements the normal way, but if it is atoms from same element, we follow this order. Don't go to this first. Go to the first one, hybridization. If that is same, go to the second one. If that is same, then go to the third one. So this order is very, very important. With that understanding, if you go to this one, CH4 given, I draw here small diagram enough, CH4. Thereafter COCl2, COCl2. Thereafter HCN, HCN. You see. Now, what is the first factor you consider? You consider hybridization. So what about hybridization here? sp3. What about this? sp2. What about this? sp. Then in the same, from the first factor itself, we can find this is how electronegativity of carbon atom increase, because hybridization S increases mean electronegativity increases. Then yeah, that's the correct order given. So that should be the answer. A-level 2021, 8th question. It is then 5th one. You see, I took long time to explain it because 5 different properties. Then each property is having different way to analyze. Some properties have different factors. You see, bond length property, different factor. Electronegativity property, different factors. Then I should explain them. That's why I took long time to explain that one. Again, we have a structured essay question, quite similar to what we discussed in the previous case also. Therefore, actually, I'll do it quite fast. No need to explain in detail. This is A-level 2021 structured essay. A-level 2021 1B. First one, draw the most acceptable Lewis dot dash for this molecule. Molecule means there is no charge. There is ClO, ClO, O. Oxygen mean double. Chlorine can pass 8, no worry. Therefore, it can have double, and single. This is 2 valency satisfied. Okay, this should be the, you know why chlorine can pass 8 more than 8? Because it's third period. That's the structure. Second part, you are asked to give oxidation state of 2 chlorine atoms in the structure. I just pass it because we have not done it. Then third part, the most stable Lewis dot dash structure for this one given, draw 2 additional one. Either O minus given, thereafter N lone pair double, N lone pair, again O minus. It's quite symmetric one. You asked to draw 2 more, you know what to do. This is the first place you have the double bond, pi bond. Okay, good. Then you can have this one because lone pair available can be donated, make the pi bond. Here also it's possible, lone pair donated can make the double bond. According to that, you can have 2 more. So if this lone pair donated, I can shift the double bond to second place in this manner. Correct? Now donated mean double, 3 were there. Now 1 donated, 2 remains. This middle nitrogen does not change. We broke this one. When it is donated, this should be broken. This nitrogen take another electron pair minus. Now I don't draw them because I explain it. This oxygen does not change, so it's minus. Got it? Minus. That's okay. This is the other structure we can draw. Next thing, to keep the double bond to third place, you know, one of this lone pair donated. We have same skeleton, NO. Since this lone pair donated double, 3 were there, 1 donated, then 2. Middle nitrogen does not change. Now this pi bond should be broken towards this nitrogen because here formed, then same side we break it. Then this nitrogen takes another electron pair minus. And this oxygen does not change, minus. These are the 2 other structures you can do. Next, complete the given table based on the Lewis dot dash structure and it's labeled. I'm talking about fourth one. Here also I don't explain because we know that one. First one, N1. If I give it like N1, they ask Vespane. 1, 2, 3. Next one, C2. C2, it has 1, 2, 3. See whether your table correct. Next, the C3. C3 means this one. There are 2 only. Next, what is it? N4. N4 mean 2 only. 3, 3, 2, 2. Electron pair geometry, they ask 3 mean trigonal planar. 3 mean again trigonal planar. This is linear. This one also linear. Right? Next, the shape around this, you know, in 2 and 1 angular. This one is 3 and 0 trigonal planar. And next one again 2, 0 linear. Next one also linear, 2, 0 linear. Yes. Linear, no change. Only first one changes. Shape around this. That's what we discussed. Sorry. Shape around this. Next, hybridization. Then 3 mean sp2, 3 mean sp2, 2 mean sp, 2 mean sp. That's the way we get it. Now they asked to complete this one. This is again a very easy part. N1F, F is the surrounding atom, terminal atom. Then it can be hybridized or unhybridized. If it is hybridized, there are 4 sp3, but if unhybridized, 2p. That is where you have lone pair. Therefore, N1 is already sp2, then it should be sp2, sp3, or sp2, 2p. Next one, N1C2, N1C2, N1C2. Yes, what is it? sp2, sp2. Next one, C2H, C2, where is C2? C2, C2, sp2, sp2. Then remember, this is oneness. Hydrogen can never undergo hybridization. right? So therefore it is terminal. Although it is terminal, we can consider hybridized, unhybridized. In hydrogen, there is no way. It's always 1s atomic orbital. C2C3, sp2sp. Next, C2C3, Harry, C2C3. Then C3N4, sp. Next, N4O. N4O mean, terminal oxygen. Then N4SP. Oxygen can be sp3 or even 2p. You see, this question repeated always. Since 2011, this question is repeated and same time. Very easy to answer. This is something given to collect the marks. Right, that's about the part 5. Let's move to part 6. That's again discussed quite fast because we have done it. Question number, part 6 I'm talking about. I think I can write it here. 6. It's about pi bond. I told you in the case of pi bond, py, pz, p and d, those are the things that can be overlapped. N1C2, whether a nitrogen carbon mean it's definitely 2p. Carbon nitrogen, in that case also, no issue. Second case also, it's 2p, and again 2p. It's actually 2py, 2pz, but no need to mention it, just 2p accepted. All right, next one, state the approximate bond angles. Approximate bond angles around N1, C2, C3, N4. So I hope you have the structure there. It is not that one. It's a different structure, but you have it. N1, once you consider N1, we had 3, then hybridization sp2, its trigonal planar means 120. But since one lone pair available, it should be 118. All right. Then around N1, you can say 118 plus or minus 1. Yes, in this year, 2021, yes, it's given like 118 plus or minus 1 given. Next one, C2. C2 is this one. Yes, C2. Yeah, C2 is this. Trigonal plane again, 120. Even 120 plus or minus 1 because environment's different. One can be greater than that, one can be less than that. I told you. C3 is this one, sp linear. So in C3 also, it's given 180 plus or minus 1. Both possible. Next one given C3 and N4. N4 is again sp. Then N4. N4 again given 180 plus or minus 1. Got it? That's the way we can have the answers quickly. Let's move to the other one. Then 8th one. In this case now, I think I explained the factors. Let's see whether we can do it. Arrange the atom nitrogen, carbon, carbon, nitrogen in the increasing order of electronegativity. It's given nitrogen, carbon, nitrogen 1, carbon 2, carbon 3, and nitrogen 4. First, tell me, out of nitrogen and carbon, which one is more electronegative? Out of nitrogen and carbon, definitely nitrogen more electronegative. Carbon should be less electronegative. Then carbon should be smaller than nitrogen. That's the point. But out of C2, C3, now you see the atoms from same element. If the atoms are from same element, to compare the electronegativity, what is the first factor? Hybridization. See C2, C3. Where is C2, C3? C2, C3, these two. sp2, sp. Then we have a very clear difference in the hybridization. sp carbon should be more electronegative than sp2. Therefore, C3 should be more than C2. Out of nitrogen, again hybridization we can compare N1 sp2, N4 sp. Again, N4 should be greater than N1. So you can have next N1 and finally N4. Got it? First we have atoms from different elements. Then we follow the normal way to find out the electronegativities. Thereafter you have atoms from same element. Then we discuss those 4 factors I explained today. Yeah, that's the way we get answer. Now we have come to A-level 2022 fourth MCQ. It's about the shapes and the geometries. The shapes, they are just shape. F3ClO, you know, Cl is the central atom because least electronegative. F3ClO mean like this, oxygen 2. 1, 2, 3, 4, 5, then 1 pair here. Then what's the shape? It is like 1, 2, 3, 4, 4, 1. 4, 1 should be seesaw. Ready? What's next one? FClO2, ClO2, and F single, double, double. 1, 2, 3, 4, 5, 6, 7. But this is 3 bonds, 3 and 1. 3 and 1 mean trigonal, pyramid. I hope you remember those. FClO3, next ClF, there are 3 oxygen. Double, 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 1. Then 6 and everything. Then tetra, 4, 0. Tetrahedral. Yeah, seesaw, trigonal, pyramid, tetrahedral. Seesaw, trigonal, pyramid, tetrahedral is in fifth answer. Correct? Here the answer is 5. Again, you have some question. I'm a question with different properties. 2022 and 7. But this is something like yes, polarizability, everything we discuss. Yes. Select the correct statement. First one, polarizability. You remember that polarizability directly proportional to the charge of an ion. Polarizability inversely proportional to the, no, again, directly proportional to the size. What you are given, F minus, Cl minus, S minus 2. S minus 2, definitely large anion plus it has the highest charge. So S minus 2 should have the highest according to these factors. Out of F minus, Cl minus, charges are same, but Cl minus should be larger than F minus. This is how polarizability changes. But what is given, it's wrong. They ask correct statement. Polarizing power of these things. Thereafter, we have polarizing power. Next one. Polarizing power directly proportional to the charge of cation. Polarizing power inversely proportional to the size of cation. We discuss all these things when we discuss the theories. Therefore, I hope you remember. Therefore, I don't discuss it in detail. Here, I explain how to get the answer only. So, out of magnesium, sodium, lithium, most charged one, magnesium. So, directly proportional. It should be the highest. Out of sodium, lithium, charges are same, then size. Lithium small mean it has high. So, therefore, it should be sodium plus lithium plus magnesium plus. This is the increase in order of polarizing power. They are descend in order. It should be magnesium, lithium, sodium, not magnesium, sodium, lithium. That's again incorrect. Third one, electronegativity of oxygen, fluorine, chlorine, sulfur. In that case, you remember the order, oxygen, fluorine, chlorine. You know the order. Fluorine is the highest, thereafter oxygen, next one nitrogen, and next chlorine, nitrogen, chlorine approximately equal, I told you. Then only other atoms comes. Right? Then sulfur comes under other atom, 3 should be the lowest. Thereafter, it should be given chlorine given, yes. Next one, it's given oxygen, and largest one, fluorine. It should be this order. SClOF. FOCLS. It's given FOSCl. That is again wrong. Third answer, it's wrong. Fifth one, the boiling point of these things. Fourth one, boiling point they ask. Then remember this one, boiling point directly proportional to the strength of attraction. Strength of attraction between particles. So what you are given CH4, CH3, CH. So these things given, this should be actually then all are covalent compound. These covalent compound exists as a discrete molecule. In that case, between two molecules, there is an attraction. That's what we consider here. Because boiling, two particles separated, this ability to separate depends on the attraction between two particles. So it is actually secondary attraction. Strength of attraction, it is a secondary attraction. So what are the secondary attraction we discussed? Hydrogen bond, dipole, London dispersion force. Those things I discussed. Now, the molecules, xenon. What about xenon? Next in boiling point directly proportional to relative molecular mass or relative atomic mass also, directly. These things we actually discussed. I think I mentioned it. First of all, we have xenon. Xenon is non-polar, atom non-polar. If it is non-polar, London dispersion force. Again, I explained in the class how to decide the type. Take the molecule and see whether it is polar or non-polar. Again, I explained how to decide polar non-polar, because we have set of shapes that comes under polar. We have set of shapes that comes under non-polar. You need to know that one. So, okay, then we have molecule, polar, non-polar. If it is non-polar, it's London dispersion force. If it is polar, check whether the molecule has HF, HO, HN bond, then it's hydrogen, otherwise dipole. Then here, non-polar atom, then LDF. Next on CH4. What about CH4? Tetrahedral means definitely non-polar. Then London dispersion force. Next on CH3NH2. You know, CH3NH2, then around nitrogen it's trigonal pyramid. It is polar. And it has NH bond. Because of that, the secondary attraction H bond. Next on CH3OH. CH3OH, you see. Oxygen, around oxygen, it's angular. Two bonding pair, two lone pair. Angular mean polar. And OH bond, then H bond. That's how we get it. Then strength of attraction, directly proportional. Then out of London dispersion force H bond, we know H bond is stronger. Out of these two H bond, which one is stronger? In that case, consider it like this. If it is H bond, see the polarity or electronegativity difference. Once you consider nitrogen, hydrogen, the electronegativity difference will be, this is 3 and this is 2.1. Once you consider oxygen, hydrogen, the difference will be 3.5, 2.1. 3, 2.1 means the difference is just 0.9. 3.5, 2.1, it's 1.4. Then OH bond has higher electronegativity difference. If it has large electronegativity difference, that bond will be more polar. If the bond is more polar, charge separation is large, delta minus, delta plus. If the charge separation is large, the hydrogen bond will be strong. Understand? So that's the way we compare. This is strong hydrogen bond. Therefore, that is the strongest one. Then CH3OH should be the largest. Thereafter, CH3NH2, the other hydrogen bond. Then London dispersion force. But then out of these two, how do we get it? Go to the size and mass actually. Because I told you London dispersion force directly proportional to even the size of electron cloud. Everything I gave you. Then size increases, LDF strength increases. Then xenon CH4. It seems like a molecule, carbon and 4, then total 5 atoms. This is just one atom, so this should be larger. No, because hydrogen first period, small atom, smallest one. Carbon second period, that's also small. But what about the xenon? It's helium, neon, argon, krypton, xenon. Helium, neon, argon, krypton, xenon. Xenon is in 5th period. 5 energy levels. Very large atom. So because of that, although it's just one atom, even the relative molecular mass, relative atomic mass here larger than this 16. Definitely it's greater than 16, because even helium 4, second member neon, it's 20. The third member, fourth member. So it's very clear, xenon has a stronger LDF than CH4. Therefore, xenon boiling point should be larger than CH4 boiling point. Is that the order given? Yes, ne? Yes. That's the correct answer. Then last one, if I say the intermolecular bond distance, again the bond length. Then NN triple bond, OO double bond. I told you then when you compare the bond length, I explain it. Yes. Triple mean the shortest. Double means next one. But the other two, fluorine and HF, those are single, FF and HF. Here the difference is this. Fluorine is common, but difference is this fluorine and this hydrogen. Out of fluorine, hydrogen, hydrogen first period, fluorine second period. So hydrogen is smaller than fluorine. If the atomic radius is small here, this bond length should be again small. Therefore, HF should be smaller than F2. But what's given? F2 smaller, HF it can't be. So because of that, 7th question, the answer should be 4th one. Try to understand the points when I explain this. 2022 structured essay question we have done, so we can skip it easily and move to the other 2024 2 MCQs and 2023 structured essay. Okay, I discuss it quickly. Seventh MCQ. It's again about the shapes. Shape. IO3 plus. So the iodine least electronegative. That's the central atom. Then IO3. Iodine 17.7. 6 mean 1 here. But IO3 plus mean that's removed. This is IO3 plus. Its shape, 3 and 0, trigonal plane. Next, NFCl2. NFCl2, then nitrogen should be the central. F here bonded to nitrogen, then there are Cl2. Yes. NFCl. Because fluorine can never be central. Then it should be nitrogen according to valencies. This is around in 1. So NFCl2, NFCl2, NFCl2. Nitrogen single bond, and 3. We have one lone pair. It's 3 and 1 trigonal pyramid. Next, F3ClO2. F3ClO2. The Cl should be the central atom. O2, F3. 1, 1, 1, double, double. 1, 2, 3, 4, 5, 6, 7. Everything. 1, 2, 3, 4, 5. 5 mean 5, 0. Trigonal by pyramid. The table. Next one, F3Cl2 array. F4BrO. Then Br should be the central atom. There are 4 fluorine. And O, there is a minus. Where do you find minus? Most electronegative atom here. Sorry, yes. Then according to that, fluorine. But fluorine should be bonded. Should be bonded to central atom. Fluorine valency 1, it's already satisfied. Then you can't put again minus. Because minus 1 mean another valency. That's why minus should come under common oxygen. Then single. 1, 2, 3, 4, 5. There should be another. This is like 1, 2, 3, 4, 5. 5. Yes, sir. 5, 1. 5, 1 mean square pyramid. Where you find that answer? Trigonal planar, trigonal pyramid, square. No. First trigonal. No. Trigonal. No. Trigonal planar, trigonal pyramid, trigonal bipyramid, and square pyramid. Yes, 5th answer. 24 again, 8th question. Select the incorrect statement. So here also different properties given. Among the chemical species, the only polar species NCl3. I think you remember the polarity we discussed. NCl3 trigonal pyramid. Trigonal pyramid comes under polar category. SO3, double bond, double bond, double bond, trigonal planar. Trigonal planar comes under non-polar category. Next one, PCl3. PCl3, PCl5, ne? PCl3 or 5? PCl5, ne? Yes. PCl5. PCl5. Then it's a trigonal bipyramid. The trigonal bipyramid comes under non-polar category. Yes, the statement correct. NCl3 only polar. It's true. The question is incorrect. Among the element magnesium, aluminum, silicon, phosphorus, the lowest first ionization energy is shown by aluminum. Variation of first ionization energies, you remember magnesium, aluminum, silicon, phosphorus. This is the order. Mg, magnesium, aluminum. This is aluminum. Silicon, phosphorus. That's the order. If you remember that, I asked you to memorize that. Variation of first ionization energies of first 20. Then they say lowest aluminum. Yes, correct. Aluminum is the lowest. Among element BCO, the lowest negative value for electron gain energy shown by carbon. What are the elements given? Boron here, group 13, second period. Carbon, group 14, second period. Oxygen, group 16, second period. All are in same period. From here to here, electron gain energy decreases. No, electron gain energy increases. Atomic radius decrease, electron gain energy increase. So then electron gain energy, the negative value for lowest negative, all are negative, group 13, 14, 16 negative. Then electron gain energy increases, mean negative value increases. Therefore, lowest should be for boron, but it's given for carbon. That one is the incorrect statement. So here the answer should be third one. Among the chemical species, only these two have same shape. Again, you can draw and then see the number of bond. You know, then NO3 minus trigonal planar, SO3 trigonal planar, SO3 2 minus trigonal pyramid, ClF3T. So this statement correct. Among these ions, lithium, sodium, beryllium, magnesium, the largest difference in size is between. In these type of cases, largest difference they ask, better you compare these things, the sizes, you know. Once I get it here, let's go to this one. Lithium plus, beryllium 2 plus, those two close each other. Then sodium plus and magnesium 2 plus. Then these two smaller than these two. These two larger. Because going down, you know, new energy level added. Out of lithium, beryllium, you know, going from left to right, the size decreases. Why? Same, same number of electrons, but nuclear charge increase, size decrease. Therefore, beryllium 2 plus should be the smallest, thereof lithium. Here also same story. Going from left to right, size decreases. The Mg2 plus should be the next one, and largest one should be sodium plus. This is the increase in order. But they ask largest difference. The largest difference should be between the smallest one and the largest one. They read the question, read the statement very carefully. They say the largest difference in size. The largest difference can be found between smallest and the largest one. Correct. Let's move to 23, structured design 1B. Draw the most acceptable Lewis FbRO3. FbRO3, the central atom should be Br. That's the least electronegative atom. FbRO3, the oxygen double, fluorine single. Then complete are the valence electrons. All right. Then don't forget to come to the central 1, 2, 3, 4, 5, 6, 7 already, no more. That's the most acceptable stable one. Second, they ask give the shape and the oxidation number. Oxidation number, I ignore the shape. There are 1, 2, 3, 4, 4, 0. It should be tetrahedral shape around central tetrahedral. Right. Next thing is the SO4 can be prepared by the reaction of SO3O3. Acceptable Lewis structure for the molecule SO4 given. Molecule mean overall charge 0. Draw the 3 more Lewis dot structure and write stable, less stable, unstable. Right. I first take the most stable one. It's given O, double S O, single low minus. That's what we have. Right. Yeah. Sulfur has lone pair. Yes. No, plus charge. It has plus charge. This has minus charge. Okay. That's the most stable one. Then they asked to draw some more structures. Actually, the thing is this one. Then double bond is found here. I can label it like 1, 2. 1, 2 is there. Then is third place possible? Yes. Lone pair available. Is fourth place possible? Yes. Lone pair available. Then you can have the combinations here. Like what? 1, 2 available already. Then 1, 3 possible. 1, 4 possible. Then 2, 3 already available. No, not available. 2, 1 available, but 2, 3 not available. Then 2, 4 available. So likewise, even 3, 4. Sorry. 3, 1 available. Then 3, 1 consider. 3, 2 consider. Then 3, 4 can. So likewise, we can have some different possibilities. I just draw quickly. Yeah, 1, 3 I try. 1, 3 mean you make it and break this. If you go to O, S, O, O, O. Sorry, you make it, then it should be double. Lone pair donated. 1, then plus, sorry. Middle sulfur doesn't change, plus this oxygen, no change. But this pi bond is broken, then here you have minus and no change here, minus, you see. That's one structure you can draw. Thereafter, I try 1, 4. Cool. 1, 4. This one. 1 keep in here. Fourth one. Then I make lone pair, make bond donated lone pair and break in this. So in that case, you have O, S, O, O, O. Once you donate double and you have 2, then it becomes neutral. Middle oxygen, no change. You have plus and O. This double cancel. I mean, sulfur takes electron here and it has another pair now. Plus neutralize because minus plus cancel. And this oxygen, no change, double. This oxygen, no change, minus. Okay. Next thing, 1, 4, okay. Then 2, 3. 2 available, make 3. Then you make the bond by donating lone pair here, but break in first. You can break the first. It should be O, S, O, 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 like this. But make the double bond between these two. There were 2 pairs, 1 plus. And here we break first one, then O minus. Middle sulfur does not change. This oxygen has double bond already. This oxygen doesn't change like this. There are 3 more. Compound Lewis structure. They draw 3 more Lewis dot dash structures. So we have drawn 3. But maybe your structures may be different because I consider these 3. Someone can consider 2, 4. Someone can consider 3, 4. And there are some other combinations. When you go to the marking scheme here, they have given 20 different structures. 20 different Lewis structures given. How can it be possible? Because they have considered this type of structure as a new one. That means, look at this one. Here, I make the bond and break the bond. That's how I go to the second one. But actually, in the case of resonance, just breaking a pi bond enough to get a new structure. Normally, it's not discussed in our syllabus, but the thing is, actually, someone has drawn it like as example, you break this only. So if you break this only, what is the structure you get? O, S, O, O, O. In the class, I will explain this phenomena. Here, no change, double like this. You break the bond mean this oxygen take another pair, then becomes minus. Sulfur loses electron plus, already plus, then it becomes plus 2. And here no change. Because I told you, just breaking, not making, just breaking. Then this is structure also accepted as a Lewis structure in that marking scheme. Actually, it is Lewis structure. When you go to the London syllabus, these structures are Lewis resonance structures. But normally we, in our syllabus, we take break something and make something. That's the way we get me. This one also accepted. So likewise, then break in this only, you can have another structure, but those are highly unstable because more positive means unstable. But they have given it 20 structures given. So better you go through that and then see it. I don't draw everything, time problem. A-level 2023, get the marking scheme and go through those structures available. But I answer according to this one. Then they ask us to write a stable, lesser stable, unstable. What about that? Plus minus. This is plus plus minus minus. This is plus minus. This is also plus minus. Then plus minus plus. What about that? This should be the stable one, because minus on oxygen, plus on sulfur. Here, this is less stable, unstable. This should be then unstable. Why? More charge separation, plus on oxygen, adjacent atom plus. Very bad. This should be less stable. Why? Plus on oxygen, compared to this plus on oxygen. This one is unstable. Why? Again, plus plus minus minus, adjacent atom plus, oxygen plus, you see. Then it's unstable. Then we have come to complete the given structure. It's very easy. I just write the answers without explaining. Vesper, then C1. What about that? Vesper, C1. This one, it should be 2. Then N2, where is N2? It's N2, it's 3. Thereafter C3, where is C3? It is this one, 1, 2, 3. Next N4, N4, it's 4. Electron pair geometry, then linear, trigonal, planar, tetrahedral. Shape, again linear, no lone pair. Next one, N2 lone pair available, angular. Next C, trigonal planar again, no lone pair. Next one, nitrogen, trigonal pyramid. Shapes, hybridization. There are 2 mean sp. This is sp2. This is sp2. This is sp3. Then they asked to decide those. I write it here. 5th one. The NC1 can be hybridized or unhybridized. SP or even 2p-sp. C1 into sp2. Next one, into C3, sp2. These things easy. Next, C3 and 4, it is sp2, sp3. sp2, sp3, N4H, co-N4. sp3, H mean 1s. sp3, 1s. C3H, C3 mean sp2, sp2, 1s. sp2, 1s. Then pi bonds, I told you the story. Nitrogen carbon mean definitely 2p. Again nitrogen carbon 2p. Next again nitrogen carbon 2p. State the approximate bond angles around C1 into C3 and 4. C1 shape also linear. What should be that? C1 180. plus or minus 1. Next, N2. N2, it's trigonal plane 120, but angular mean one lone pair. And then it's 118 plus or minus 1. C3, trigonal planar, then no change. It's 120 plus or minus 1. N4, tetrahedral trigonal pyramid mean tetra 109, but one lone pair trigonal pyramid. It should be 107 plus or minus 1. Plus or minus 1. Next, arrange the atoms in the increasing order of electronegativity. Again, carbon, nitrogen higher, carbon less. Out of C1, C3, sp, sp2. sp2 should be small. S smaller than sp. Out of nitrogen, sp2, sp3. sp3 should be smaller than sp2. So that's the answer for the 8th one. Hybridization. Order is hybridization, formal charge, oxidation state, and finally electronegativity of bonded atom. But from the first hybridization, we could get the arrangement. That's the end of the discussion of homework sheet 2, structure and bonding. These points I discussed today will be really helpful to answer the questions in unit test. So therefore, go through this several times. Okay, that's enough then. See you in the class with the unit test.